joining this webinar, Energy and Nuclear Power. The material I'm going to go through is some offered at the Evergreen State College in Olympia, Washington in 2007 and 2009. Designed for upper division who'd had work here in environmental studies or political economy. And in them was to talk about the picture of energy. The most was that environmentalists are very accustomed to being with climate as an energy problem. Usually the discussion goes something like the carbon dioxide that goes into the atmosphere comes from the fossils, and therefore we do something besides burn fossil fuels. But the point the discussion seems to end. And I thought it much further. We have a lot to hit only the highlights. The talk will take somewhere around 35 minutes. My background is in the biological sciences and in environmental history and history of technology. Sciences, which I draw upon as much as I could, and material does reflect my own background. And I think it's going to be common with all energy courses that the background of the faculty will have a tremendous effect on what is actually covered. The talk is first a framework. In order to energy and climate change, it's very important to have an intellectual framework that can get to what the big picture looks like. This what about nuclear power? Is it creating technology for climate change or not? And some of the teaching tools used for this that with energy as an issue in climate change. And there are convergence energy flows and carbon dioxide flows of alternatives, field trips, and transition. Change basically is an energy problem. It's difficult to imagine any sort of the climate change impacts without doing major overhauls of our energy economy. And the task that is in front of us, framework. We have to have orienting our thoughts about what we're going to do and why, what we need. Studies, not the original name, it's intensely interdisciplinary. In the field, although it has very few recognitions of degrees and that sort of thing. I think change in the years to come, but at the moment, it's still an experimental disciplinary field. As discipline has all authority and to bring in multiple perspectives. There are approaches that one take to developing this is one that the interdisciplinary nature can be addressed, that individual teachers gain breadth and go beyond the comfort zone to learn new things and to bring new things to their students. And in colleges, it will take multiple departments and schools to material. Likely no one model that fits all institutions. So every faculty who delves into this will have some their own particular circumstances. About the element of the framework. This to be a core. definitions, theories, methods, accepted factual bases. Can't cover everything, and so you need to know where to draw the line and say, okay, we've done as much as we can. We should try to bring any more issues in. I also found that is best an effort that involves multiple layers. Around each individual faculty that embraces the subject, own layers based on their own experience. And the explicit link of climate change to energy. Let's start with definitions. Many of these come from the physical science because the way I approached energy studies was really to make them more based on physical concept. And in mechanics, we know that energy is the ability to do work. Several kinds of energy: kinetic energy, the energy of body, mass in motion, type of energy, where fuels come in. Primary fuel is something that can produce motion or heat and thus can do work. And is the energy stored in a substance that can be released. I took them some very elementary introductory physics material to show how these definitions generated units for measuring energy. I have some core theories about what this was all. Two of these come straight from the physical sciences, the laws of thermodynamics. Energy is conserved, the first law, the conservation law, and 100% efficient. Entropy, heat dissolved with no useful work. There are most the first and second law, whose background is in the physical sciences, either physics or chemistry. More precise talk about this, but for the students I worked with and my own background, this is part of what they needed to know. That heat and motion are interchangeable. They are both forms of energy, kinetic energy and heat. And the theories begin to move away from the physical sciences because from the transformations of heat and motion, we reach technologies that give us industrial civilization. It's from engines, from mobility as something we take for granted. We also from electronic communications and data management, and an industrial economy working without rich energy services to sustainability. There's a very wide understanding of what the business is all about among citizens. Used really moves away from the physical sciences is that humans capture energy transformation, and this is both biological, ethical, and political economic considerations. Players start adding on to the of physical sciences. Disciplinary fields do not mean that disciplinary methods are left behind into a different context. And faculty members' expertise and background, methods that will show up in energy studies courses could come from the physical and biological sciences, the social, the humanities, and the arts. I think we forget the arts because energy design and aesthetics, as well as physics and economics and politics. In fact, I had students who were interested in the arts, and they added a very interesting dimension on with the material that we covered in the courses I taught. Methods. There are methods that come out of the government's legal scholarship that are useful and important. There are even decision-making methods that don't necessarily belong to any particular discipline, but find wide application in multiple settings. Methods is that quantification is necessary. It's not, but it's not necessary in energy studies. That I dealt with was basically arithmetic, percents, and powers of 10. This is very complicated mathematics. I found it worked with readily embraced and were quite skillful in all these simple transformations that we needed. Others really didn't feel comfortable, and I had to work and push them on this method. That I think belong in a core. First, several are really just accepted to come out of the physical sciences. If you want fuels, you get heat and you get work. We all sorts of things with the heat. Yields heat and thus work. And thus made into heat and work. Heat captured from solar radiation, winds, moving water, and the interior of the Earth. The core accepted facts that I used. First, I don't think will be a surprise to people in this webinar. It's real. It's not a hoax. A week and a half going to climate change to why it was real and how it linked to energy, and to impart to the students the notion that it was a subtle process that is intuitively obvious, but it has numerous implications for the future and implications for what we do about energy. The fact that political crisis is often associated with energy. Oil in particular. Iraq. Imagine the First and Second Persian Gulf Wars without oil as a factor. There is the question of our fossil fuel use are we at our ability to get these things out of the ground and burn them. Particularly into costs. The more people are willing to pay for energy, the more fuel that you can find. And heating also brings in wind. The point that we're going to run out of either oil or coal, gas in 1 or 2 days. But centuries, the question becomes different, and it is an important issue. One of the things I think is very important in energy studies is to try the students of the bounds of this field lie here. And I want to give credit to my colleague Rob Knapp at the Evergreen State College, who introduced me to these energy flow from the Lawrence Livermore National Laboratory some years ago. An interesting graphic. And as I thought more about it, I thought this is an important graphic for giving students a sense of the economy or the energy budget of a particular time and place looks like. The energy economy or energy budget for the United States in 2011. It says up there at the top that we used approximately 97.3 quad energy during that year, according to the 15th BTU. We'll come in a few minutes. Is that if you look on the left-hand side, you will see fuels, and there are not very many of them. Solar, hydro, and so forth, down to petroleum. Width of came from each fuel. What, of course, is that petroleum, gas, and coal are the big three, and number four. An important transformation, some directly to the services, which you can see on the right, the residential, commercial, industrial, and transport, but electricity is an enormously versatile way to carry energy. On the side, you do see the four sectors of the economy as to where energy is used, and you can see how quads go into each sector. Over on the far right, you see two numbers. One is the energy services, the useful work we get from the fuel that waste heat. And it's instructive to notice that the majority of the energy that we use actually ends up as heat, which part is not made use of. It goes to waste. I think about this graph is it needs to be seen as a dynamic thing. In graphs over a period of years, you would discover that the shape of the graph changes, sometimes quite strongly, and other times from year to year. 12, when it's produced sometime next year, will have a little difference, and in particular, natural gas going into electricity and coal will be smaller. These graphs change, but the graph shows the boundaries of what we need to know about within energy. The energy studies is very much tied up with layers. So I put the core of the physical sciences at the center. The graphic on the energy economy or energy budget would be the next route. And succeeding layers, I think, will be from personally, as they develop their courses in energy studies, they used a lot of examples from history and political economy and ethics to form outer layers. Question of linking climate change to energy. And I basically translate from the graphic on the energy economy to something about carbon dioxide emissions. This is drawn from the year 2007, which was the peak year of U.S. energy use. It's declined since then because of the economic recession, but from 101 in 2007 down to about 97. So we lost 4% of our energy consumption due to the recession. But over on the left-hand side, big three. That's where most of the quads that we use. Nuclear, and then the hydropower, biomass, and thermal wind and solar, that's the GWS, provide in that year very small amounts. By then, the Livermore National Laboratory had developed, these all come from the Energy Information Administration. Was emitted, and here we emitted almost 1 million tons, about 6 billion tons. Okay. Energy requires reducing CO2. The lack of that would set up a system of trade passed the House of Representatives in 2009, and it called for an 83% reduction of carbon emissions over a period of time. It's 80% reduction, and said if we emitted 56 million in 2007 and we reduced this by 80%, we could 85, about 1,200 millions or 1.2 billion. How are we going to reduce it? Well, it's the most quads for the least oxide. So keep all the gas you can, and eliminating all petroleum, all coal, and some of the gas to get an 80% reduction in CO2. And quads are left, and it took about 30 quads. Now, 2% reduction in the energy budget, and there are no ways of mitigating the catastrophic impact this would have on the nation. Carbon capture and storage technology will be developed. Because it's not yet in any sort of commercial way at a scale to make a significant difference, may change in the years to come. Efficiency could drastically improve quads to get all the services we need. But on carbon capture and storage and efficiency, it's unlikely that we can gain quads to keep the country running at a process of standard. So one of the alternatives that emits much lower carbon dioxide emissions has to be up. We need new supplies. Are those nuclear, hydropower, biomass, geothermal, wind, or solar? Hydrokinetic, using tides, ocean currents, waves. I think we revised this chart. The hydrokinetic will appear, but it's just starting to make an appearance. And if you think, why climate change is so difficult to solve, I think this chart really captures why it's difficult to chart. To hold up is that a 60% reduction in the energy budget of the country would be catastrophic. Nobody is proposing it. There applies that something has to increase, and if it, and perhaps carbon capture and storage. So this that shows the nature and the magnitude of the challenge. Now, and there are many people who believe that nuclear should be and can be a very good mitigation strategy. Maybe entirely, maybe other things are also needed, but certain solution. And so, regarded as one of the most important, of course, is that rather than go lengthy arguments about whether nuclear is or isn't a good source, the problem is to find out and be able to articulate the strengths and weaknesses of each alternative. So, strengths, it's the largest alternative with low carbon emissions. It can provide base power that we could electrify transportation and not rely on oil. It is the utility industry. We have a lot of experience with this technology. It has established regulatory infrastructure and is avidly seeking the renaissance. It has safety and costs as the two difficult issues. The accident of 2011 certainly reinforced the notion of safety. And cost is important because the capital costs of nuclear power are so high up front. And in the private sector has given quite clear signals that without guarantees from the federal government, just won't touch this technology. It's to involve either a private partnership or, in fact, it has to be a federal undertaking. The United States would have, if it was serious about nuclear again, would upgrade its manufacturing capacity and its educational infrastructure, which, as I mentioned, is extremely large for nuclear. That requirement would compete with other alternatives. Capital needed to invest in solar or wind or geothermal or hydroelectric technology. So we won't get into all of the, what's been all this, but to me, what this weaknesses means is that energy studies is really about making strategic choices. You need to decide what they think is the best choice, and it is cognitive and cognitive dimensions. And the fact that like ethics and aesthetics are very important. Talk about teaching tools. And some of the resources that I've put on the slide and that will be available on the CAMEL website once they're put up, will be these tools. I through understanding the metric and the English units and heard them. And some of the resources I've provided are exercises that take you through this. The reason I go over the units is that it's impossible to read the energy literature on the units unless you understand how to convert from one. It's arithmetic operations, but students needed to understand the units to literature and to understand the magnitudes, because modification of magnitudes is really important. What is in 62 quads of energy if we carbon dioxide emissions by 62%? Our graphics from Lawrence Livermore National Laboratory. This is the energy flows, and the second is the one that carbon dioxide flows. If you know has all the energy sources and flows, of course, shows that for the most part, the gas coil that produce the carbon dioxide. These two graphics, in particular the energy flow ones, are orienting the term. Every time I turn to a specialized topic, I would bring up energy flows, and they're here in the chart, and I would point to exactly where in the chart we were discussing. Dioxide flows is very useful for reinforcing the notion that in terms of their carbon dioxide flows. The teaching tool, when we came to the energy flows, very early in the term, students really spent some time in a workshop format going traffic on energy flows to make sure they understood what it meant about the total flow of energy, the primary flows, the transformations, the desired energy services, what the area was, the U.S. 2011, and the energy lost as weight heat. Exercises, basically proportions, and learn that energy specialization exists. For example, petroleum goes primarily for transportation, and the most versatile of the fuels. Some fuels, nuclear, go only to electricity, and so they need a sense of different fuels and their specializations. And orient all lectures, all discussions. When it choices, I tried to introduce the notion that there are a multitude of methods that could be used. Some want to develop some of these methods in quite depth and vigorously. I to approach the methods more closely, that they were considered each method a little bit different about the technology. It doesn't tell you everything. You really combining multiple methods to find out those factors that you think are most important for making strategic decisions. One of the courses I taught was that field trips were absolutely essential. Students have never seen these installations. They are awe-inspiring, regardless of what they are. To high power dams, Washington State has lots of them. Wind installations. We also went to a large coal power plant just south of Olympia. It's possible with much lengthier field trips to go to oil refineries and nuclear power plant. I didn't go to those facilities. One on the potential list for field trips are independent system operators, the installations that manage the electrical grid. And in some states and locations, they might be very interesting in field trips. Of course, we're